Good evening, my name's Mike Hewson. This is my very first produced and published YouTube video. I've chosen to have a new channel and I'm going to call this channel Mathematics Bites. The purpose of the channel is to give bite-sized pieces of mathematics for people who are in a hurry perhaps, or for those people who have learnt the mathematics a long time ago and have forgotten, or maybe you're learning for the first time. So we don't want to get bogged down in the weeds here. We want to give a general overview of what goes on. Today's topic is the natural logarithm. Now, John Napier, a Scotsman, about 400 years ago, invented the idea of a logarithm. And a little later, with some help, he came up with the natural logarithm. The natural logarithm hinges on a particular number. This number is indicated by the lowercase letter e and is approximately equal to 2.71828. This number actually goes on with infinitely many non-repeating decimal digits and is a transcendental number. That is, it is not the solution to what is called an algebraic equation. We won't go into that anymore, but file that away in your mind, that e is a transcendental number. Now, back in John Napier's time, there was very little mechanical assistance to calculating. Calculations were done by people called computers. They could make a living out of performing calculations for people for a fee. Now, if I was going to multiply two numbers together today, I'd obviously just use my own computer or a pocket calculator. But back then, it was much harder to multiply numbers together accurately and quickly. So you can view this technology as forming a basis for a lot of further work in maths and physics and in other areas of the academic world. The fundamental idea is that a logarithm can turn multiplication into addition. Now we're going to learn both the natural logarithm and the exponential function at the same time. These functions are inverses. What one does, the other undoes. And if you look at the graph, you can see that the bottom left, the curve for the logarithm of x, is a mirror image of the upper left curve for e to the x. This is deliberate. Now it turns out that you can extend the idea of logarithm to other number types, in particular the complex numbers, but that's a whole other topic, so we won't get into that today, but it does have a generalization. If, for instance, we look at the number 20, well, that is approximately e cubed. I can state that in another way, and that is 3 is the natural logarithm of 20. Those statements mean the same thing. A couple of key facts about the logarithm function. you'll notice that you can't get a logarithm defined for the number 0 or any number less than 0. And that is paired with the fact that the exponential function doesn't produce an output which is equal to 0 or less than 0. The natural logarithm curve crosses the horizontal or x-axis when the value of x equals 1. So I would say that the natural logarithm of 1 is 0, or that e to the power of 0 equals 1. These are essentially equivalent statements. The other feature of the natural logarithm is that the natural logarithm of e itself is 1, or, again equivalently, e to the 1 is equal to e. Now, let's look at specifics. So to make these logarithm ideas a bit more concrete, I thought we'd do a couple of straightforward examples. I've just picked two numbers off the top of my head, 4.628 and 7.934. And suppose I was asked what the product of these two numbers was. Now I could do that by long multiplication, or rather I probably couldn't, in the sense that I'd probably make a mistake and have to do it several times and recheck it. In the end I'd probably get a calculator out and get it done for me. But suppose that we're living 4 centuries ago and we don't have such mechanical assistance. What would a human calculator do, given that they had access to logarithm tables and also to anti-logarithm tables? Well, first thing you'd do would be to look up the logarithm of 4.628 and you'd get the number 1.532. Write that down. Then you'd look up the logarithm of the second factor, 7.934, and you'd get 2.071. Because I wish to multiply the two numbers together, I'm going to add their logarithms, and I'd get the result 3.603. Haven't finished yet though. To finish the problem I have to do that inverse step where I do the anti-logarithm, or the exponential if you like, raising e to the power of 3.603, and I would get the number 36.708. We can tell this is a reasonable answer because some number a little bit less than 5 times a number a little bit less than 8 is going to be a number a bit less than 40. So that's all quite good. Notice the two things: A, it can be done quicker, and B, it can be done more reliably. So we added logarithms to get the multiples there. What happens if we subtract one logarithm from another? Well, what you get is one number divided by another. So we'd still look up the logarithms of our numbers, the logarithm of 4.628 being 1.532, the logarithm of 7.934 being 2.7071, but this time we'll subtract 2.071 from 1.532. This gives us the answer minus 0.539. Now the first point is don't panic about the negative number. That simply means that you're dealing with a number that's less than 1. Now if I look up the anti-log tables for that number, I will get the answer 0.5833, that being the quotient of 4.628 with 7.934. So you can see this is quite versatile. Just before we finish, I'll ask two questions but not answer them, at least not today. What happens if I take the logarithm of a number and then, for instance, multiply that logarithm by 3? What have I achieved by doing that? I could also ask the question that if I take the logarithm of a number and divide it, say, by 2, what have I done ultimately? Now I think that's enough for my first YouTube video. My apologies for any dog barks you may have heard in the background. Young Murphy is merely a puppy and he gets a little bit hungry this time of night. Now this video was produced with the Movavi video suite. The pictures were produced with Microsoft Paint on a Microsoft Windows 7 machine, and of course we should thank YouTube for hosting it. Good evening.